All right, good morning, everyone. So my name's David. I'm a third-year PhD student at UWA, and so I'll be discussing some of the improvements we made over the past year in improving hydrate phase boundary predictions. And so this is going to be covered in two general sort of themes. So firstly, I'll be walking through a new conceptual hydrate model that we've developed that has 40% fewer tunable parameters, and this comes with an improved physical basis in the theoretical side, and I'll discuss the result and how it maintains accuracy for multi-component gas mixtures. And secondly, I'll be talking about some of our initial efforts to extend this hydrate model to model complex reservoir fluids that have heavy hydrocarbons, where in our initial attempts we have some good results with an average deviation of less than 1 Kelvin without any significant tuning to the heavy hydrocarbon modeling. And so just to bring this back into context, so we care about the hydrate phase equilibrium curve because we use this to try and map out the regions of a pipeline that are going to be at risk of forming hydrate. And so by plotting the equilibrium curve, we can see that these regions are within the hydrate forming region. But of course, with these hydrate equilibrium models, there's going to be an associated uncertainty associated with the predictions. And so two quantities we care about in particular is the average absolute deviation, which gives us the overall inaccuracy of the model, and the bias, which is going to tell us the conservativeness of the prediction. So whether it's going to underpredict or overpredict the equilibrium temperature. And these quantities are something that are going to change with system fluid composition. So compared to the system with no MEG added at all, when we add MEG to shift the hydrate equilibrium curves to prevent hydrate forming in the pipeline, your deviation curves are going to change. And of course, when we have the systems that have high weight MEG percent, there's going to be less available experimental data to compare against. And because of that, we're not going to be as certain in those margins here that we can apply. And so in the past, I talked about how we can leverage experimental data and the comparisons against models to use these quantities of uncertainty and bias to reduce the safety margins that are applied in industry. And today I'm going to be talking about how we can also improve the hydrate equilibrium models and reduce the overall uncertainty associated. Because if we can reduce the amount of MEG required by understanding the margins of bias and overall inaccuracy to apply an under-inhibition strategy, we can reduce it by 4 or 5 MEG percent, and we can get significant reduction in the cost required. But in terms of the capex, we have less MEG required, then we're going to require smaller facilities, and then the MEG injection and regeneration with smaller weight percent MEG is also going to be lower, and you're also going to reduce your associated carbon footprint. So in terms of what hydrate model consists of, so the big breakthrough was with Ballard and Sloan in the implementation of CSM-GEM back in 2002, and the model I'm going to walk through today is based on this. And Hilscher built upon this model by improving the description of the empty hydrate lattice. So these are some sort of the namesakes in terms of hydrate model literature. And in terms of the features we're concerned about with hydrate modeling, there's two main parts. So you have the empty hydrate lattice description that's sort of independent of a free water phase. And secondly, we have a description of how the gas molecules actually occupy the hydrate cages. So we're looking at the physical geometry of the hydrates themselves, as well as the intermolecular forces between the gas and water molecules. And so what I'll be walking through today is sort of the basis of these two models and how we've improved them, because they're currently over-encumbered with an excessive number of tunable parameters. So starting from the beginning, we're looking at the basis of the classical hydrate model. So this is the model first developed back in the 50s. And when we're looking for hydrate phase equilibrium, or the stability of the hydrate phase, technically we're looking at this chemical potential difference of water between the hydrate and the liquid or the ice phase present. So when you have water and gas molecules such as methane at the right conditions to form hydrate, high pressures, low temperatures, there's two steps of formation that this model considers. So firstly, the formation of an empty hydrate lattice, which has an associated energy change with this term here. And secondly, the stabilization of this lattice to actually form the hydrate in terms of how the gas molecule occupies the various cages. And so what the new model that I'm presenting today is focusing on is the occupation of each of these various cages within the gas molecule occupying each of the various cages. And so the key term we're focusing on is the fractional occupancy, which gives us the probability of a given cage of a hydrate being occupied. And this is informed by something known as Kihara potential parameters. And so these parameters describe the intermolecular potential, or the forces between the gas molecule and a given water molecule that makes up the cage. So we'll dive into this a bit here. So this is a schematic of, say, two molecules that make up a given pair. And this is how the occupation of the hydrate is primarily informed. And so if we look at this graph here, this gives us how the intermolecular force changes over time and relates to these Kihara potential parameters. So firstly, you have this parameter A, which is the hardcore radius. So this is the minimum distance that the pair of molecules can approach each other. So they can't get any closer than this. If you go a bit further apart, then you reach this parameter sigma, which is the distance where there's no net attraction or repulsion between the two molecules. Finally, if you go a bit further, you'll reach a distance where you have your maximum attractive potential between these two molecules, so where the attractive force is the greatest, and that's the parameter known as epsilon, the well depth. And so if we continue to push these molecules apart, then eventually the attractive forces will dissipate. And so these three parameters are known as the Kihara potential parameters, and typically we have one set of these parameters to describe all gas-water interactions in all the cavity types of the hydrates. And so if we consider that this is only for one gas-water pair, hydrate cavities can have 20 to 30 water molecules and one gas molecule, and it becomes mathematically complex to try and sum all of these interactions together. And so a simplification that's made in doing this is we assume that the cage is a sphere. And so we assume that all the water molecules sort of lie on the outside of the sphere. So depending on the position of the gas itself, this simplifies the calculation needed quite greatly, because we don't really care about the angle. We can only really care about the position of the gas molecule. So this allows for integration in one dimension, and it allows for much simpler mathematical calculation. But of course, this comes with some drawbacks, because the cavities themselves are not spherical. They're going to be asymmetrical, and the cavity types themselves are also going to have an influence. So the shape of the cavity, the size of the cavity, the number of water molecules that make it up. And so to account for the fact that the gas-water interactions are not going to be the same in the cavity types, even though we use one set of parameters for each of the type, over time there has been this development of a concept of a multi-layered shell. And this multi-layered shell splits up the cavity into 3 or 4 different layers or radii. And the idea is that we account for the potential asymmetry of the cage that the spherical assumption doesn't account for. And we account for the fact that larger gas might distort the cage as well. And so the problem with this approach is that you add a significant number of parameters, because instead of having one layer to consider, you need now you need to consider 3 layers, each that have their own associated set of parameters, and you're also going to increase the number of calculations required. And so part of the improvement that our work produces is that we're reverting back to a single shell where we have one layer with an average radius, and this greatly simplifies the contribution to the occupancy calculation. But if we revert back to a single layer, how do we now account for the fact that the interactions of the gas with the water molecules of the cages are going to be different in the cage types? Because this development of a multi-layered shell was meant to try and capture that. So each cavity type would have a different discretization of the multi-layered shell. But if we're reducing it back to a single shell, how do we now account for this? And this comes back to the fundamentals. So we're looking at Kihara potential parameters themselves. So firstly, just remind you of structure 1 and structure 2 and the various cavity types. So hydrate cavities have small and large cages. And in this case, structure 1 and structure 2 have the same small cage type and a different large cage type. And so the concept here is that we leverage the fact that the structure 1 and structure 2 hydrates share the same small cavity type, and then use the difference in the large cavity to capture how the gas will interact differently in each of the structures. So to walk you through it, so before we had only one set of Calc potential parameters that modeled the interactions of the gas in all of these cavity types, but now we're looking at modeling each cage type or cavity type with a separate Calc potential parameter set. So we consider one Calc potential parameter for the small cage that's common to both structures. If we want to model structure 1 hydrates, we then consider a separate Calc potential parameter for the large cage. So we want to model methane or carbon dioxide hydrate, for example. And then finally, if we want to model structure 2 hydrate, then we'll have a separate Calc potential parameter set for that large cage associated with structure 2 hydrate. And then this could be extended and so on for structure 2H. And so by removing the concept of a multi-layered shell and instead focusing on the gas-water interactions and how they differ in each cavity, we've actually achieved a significant reduction in the number of parameters needed. And so from the original Ballard and Sloan model, that was the first skipped energy minimization, we've improved on that and reduced the number of parameters from 103 to 64, about a 40% reduction. So now let's walk through how does this performance actually hold up in practice when we're looking at calculating the hydrate equilibrium temperature. So first we're looking at simple hydrates, so hydrates that only have one gaseous component. So we're looking at a very restricted range of data, but that's relevant to industry, and we're comparing against CPA hydrates as implemented in Multi-Flash 7 and Ballard and Sloan as implemented in CSNGen. So firstly, I want to, focus on the overall performance. So here we can see that this work performed on par with both Multi-Flash and CSNGen and outperforms the intermediary Hilscher model that's been published in literature that has a different data set. With individual components, we see that our model performs quite well for methane and ethane hydrates as well as carbon dioxide, but it doesn't really perform as well for the structure 2 simple hydrates as propane and isobutane. But we can see that there's good performance for simple hydrates at this point. We then look to a summary of the overall behavior across various systems, so ranging from pure gases to binary gas mixes to multi-component gas mixes. We can see that the overall performance of our model is on par with both Multi-Flash and CSNGen, where particularly for multi-component gas mixes, we can see that our model performs slightly better than Ballard and Sloan or CSNGen and slightly worse than Multi-Flash, but the deviations are not that significant at this stage. And so this is quite a substantial improvement while reducing the number of associated parameters. If we then looking at systems that have inhibition, we're mainly looking at systems with MEG at this point. So ranging from pure methane all the way to multi-component gas mixes, we can see that the performance of the new model presented here is very good compared to Ballard and Sloan, CSNGen, and on par with Multi-Flash, on par with Multi-Flash at this stage. And further improvements for these type of systems will come with more experimental data that can improve the hydrate model itself, but we want to improve the accuracy for MEG systems in particular. Then we're looking at optimizing how we predict the fluid phase. And so the point that I want to highlight here is that even though the performance might just be slightly worse than Multi-Flash at this point, with our model, we know exactly what's going on. Our Multi-Flash is a black box, and so we can always make improvements to our model, changing the parameters we use or the tuning methods that we use to always make improvements and see how the tinkering that we apply to the model will change the performance. And so this is a quick demonstration of the calculation within ThermoFAST 2. The new version will be available soon. So this is looking at a 4-component system with water and as well as MEG inhibition. So looking at about 25% MEG here, 8% that is. And so we also have our old iteration of the model here that we used that presented on previously, and then we can plot the hydrate equilibrium curve. and we can copy the data for use elsewhere. We can copy the graph as shown. So now I want to talk about how we can extend this new model that I presented to account for the complexity of industrial fluids. And when I'm talking about industrial fluids, I'm mainly talking about fluids that have heavier hydrocarbon present, so your heavier oils or your natural gases that aren't as light. And so firstly, let's look at this table on the right. So as the number of carbon atoms increase, you can see that the number of potential isomers is going to increase exponentially. And so when we consider reservoir fluids that have a significant amount of these heavy hydrocarbons, it becomes impossible to define the key parameters that is required for each of these components to use in an equation of state to model the fluid phase. And so what we do is represent hydrocarbons with more than 7 carbon atoms as CETA components. So we represent all those potential isomers as one sort of component with a fraction. So you might represent all of your C8 isomers in a C8 fraction, and then all your C20 isomers in a C20 fraction, and so on. And so why do we care about CETA components? How is this relevant to hydrate modeling? As it turns out, CETA components themselves don't affect the hydrate model directly. And that's because the components associated with these heavier hydrocarbons don't occupy the hydrate cages. But they do influence the hydrate phase equilibrium by changing the properties of the fluid phase. So how the methane and the propane will interact with the heavier hydrocarbons will affect the resulting hydrate equilibrium. And so proper characterization of those heavy hydrocarbons is necessary to try and capture hydrate phase equilibrium when you have those heavier hydrocarbons present. And so the way we can do this is primarily through gas chromatography, alternatively distillation. And so with gas chromatography, this is an example on the right, when we're considering trying to characterize the different components based on their boiling point, for example, as you pass the sample through a tube here, the heavier component will be slower than the lighter component, and you get the separation based on their weight or their boiling point. And so once we can characterize a fluid into these separate carbon number fractions, then we can use various pressure volume tests to further verify the composition, such as constant volume depletion and constant mass expansion. And the point here to highlight is that if you want to have a fluid from your field experimentally measured and as part of hydrate phase equilibrium model, then we have the capability at EWA to perform these types of measurements with gas chromatography to get the fluid composition and then characterize the wax and deposition as well as the properties needed to implement it in the hydrate model. So let's look at some examples of hydrate phase equilibrium that had these heavier hydrocarbons present. So firstly, we're looking at a fairly heavy gas condensate. So the methane fraction is quite light, so it's less than 80% here. And we have about 7% of the mixture being consistent of heavy hydrocarbons. And so the only information that we have in this case is the molar mass. And what we can do is we can use this information about the molar mass to generate a distribution of each of the single carbon number fractions all the way up to C26 in this case. And so this is using quite a limited amount of information in terms of the reservoir fluid. But we can see that even with this limited amount of information, in terms of the hydrate equilibrium curves that we generate with ThermoFAST to, compared to the measured experimental data and multi-flash, we get a very good prediction of the equilibrium, and in this case, where we get agreement that is quite good with both experimental data and multi-flash. We then look at another system. So this is data from an old GPA report from the 80s. And here we can see that the composition is much more detailed. So you have some BTEX compounds specified, and we're given a more detailed analysis of the composition of each single carbon number fraction up to C27. And so here we're actually looking at quite a range of systems. So ranging from no inhibition to up to 58% inhibition with both methanol and MEG. And here we can see that ThermoFAST performs quite well against experimental data and multi-flash, but just slightly worse. So interestingly, in this 25% case for MEG, multi-flash actually doesn't converge quite well, but that's the correct structure. And in terms of the drawbacks of ThermoFAST 2, you can see that at 58% methanol, the deviation is higher for these high pressure points. And that's because we're still working on improving our BLE flash for these high concentrations of inhibitors. And this is also caused by the predictive nature of the model in terms of the vapor-liquid equilibrium. So multi-flash has some method of generating the binary interaction parameters needed for these acidic components with the water and the MEG and methanol. But we currently don't have that implementation. But we can see that even without those improvements, in our preliminary work in trying to model these complex fluids, ThermoFAST 2 is performing quite well. So now I'm going to show a second demonstration. So this is just showing how we can define acidic components within ThermoFAST 2. So you can enter properties such as just the carbon number, or if you have more detailed information, the molar mass or the specific gravity. Or you can also just generate a batch of them based on the carbon number, and you can see you generate all the critical properties needed using the EOS. So we can save these properties and use them for later. So I'm actually just going to load a predefined mixture here. So one of the examples from the previous slide, and you can see that we have all these components with the composition prepared here. So there's 25 weight% MEG. We do a calculation here, for example, so you get the hydrate equilibrium temperature and all the phase properties and compositions. So just to wrap up, so today I presented a new hydrate model that's been able to be extended to complex reservoir fluids that have these heavy hydrocarbons, and in terms of the predictions for multi-component systems on par with multi-flash, it's not slightly worse. And the way forward from here is how can we then begin to improve these predictions? What's the way path for doing that now that we have this new physical basis? And the path forward really come back to tuning. So how we apply tuning strategies and how do we develop a model that can automatically retune itself? And so why is this desirable? So having a model that can be readily tuned, so say having a tuning interface in ThermoFAST 2, it helps enable flexibility and it improves the prediction accuracy. And this is particularly important when you're looking at specific data subsets. So let's say you're looking at like a high content field that has a lot of carbon dioxide, for example, then we can look at improving our parameters specific to multi-component systems that have a large amount of carbon dioxide, and maybe you're interested in a specific pressure and temperature range, then we can also begin to tune parameters to that specific range as well. Secondly, it also ensures that the model performance is up to date with trending experimental data. And so the idea is that if you're aware of new literature data that hasn't been included in ThermoFAST 2 or part of the tuning process, then you could enter that data itself, update the parameters, and see how does the model performance improve for various other systems. And of course, if you have your own fluid data that hydrate equilibrium data that you'd like to get included or measured at EWA, then we can take those measurements and also include them in our model to improve the performance. So that's the general way forward from here. So how to improve the hydrate equilibrium model we have. So that's it for me. I'd like to acknowledge my supervisors, Peter, for helping out with ThermoFAST 2 software side, as well as the various sponsors, KBC, for providing the multi-flash license. Thank you.